Annenberg Media.
Why, when I look in this mirror, do I see Alex instead of myself?
Why can I see myself in the water? When I put my oar in the water, why does it look bent?
Welcome to the second session in the series Shedding Light on Science. I'm Christine Jones. I'm an astrophysicist at the Harvard-Smithsonian Center for Astrophysics in Cambridge, Massachusetts, where I carry out research using X-rays.
And I'm Anita Greenwood, a science educator at the University of Massachusetts Lowell. Part of my work is with graduate students who are becoming elementary teachers.
Last time we described light as tiny packets of energy called photons. We explored the idea that light travels in a straight line very fast, that shadows are formed when an object blocks the path of light, and that we see when light is reflected from objects to our eyes.
Today, we'll continue to explore what happens to light when it strikes different objects, how light photons are reflected, and how light photons are refracted.
Here we are in our darkroom. When it's completely dark, we can't see, but with our flashlights, we can see objects in the room. Light travels out from our flashlights to the objects and then is reflected from them. For example, from this toy elephant, or from that poster. So if light reflects off objects, why do we only see reflections in shiny objects, like in that mirror? Let's begin to explore this question by looking at reflections in mirrors.
Yes, sir. How many do you have?
I have two. And on the outside is a big multifaceted like ball or star.
That works with
These teachers are exploring various aspects of mirrors.
11, 12, 13, 14. No, I count about 15 on each side. I count 30.
He's trying to do one
There's
up.
50. Well, I closed one eye so I could get a better
Pass it
read.
over to her. So here, okay, here.
Exploring reflections in mirrors is a common experience in elementary classrooms.
How do you get anything? And then after we experiment with 90, we'll be changing the angle, opening and closing.
Jackie, I'm getting suspicious.
Now, we've promised to look behind the activities to the science, so let's do that.
I'm going straight. Go. There. Okay, I can't really see me. Can you see me? I'm going straight.
We asked Joe and Terry to stand on opposite sides of a table. We then asked Joe and Terry to arrange their mirrors so that Terry can see Joe's reflection in her mirror.
Oh, I see you. We see you.
After some trial and error, the children figure out a way to solve this challenge. The children quickly learn that if they place themselves directly in front of the mirror, their image is reflected straight back. They discover that they must arrange the mirrors so that light from Joe's face is reflected in such a way that it can be captured by Terry's mirror and reflected into her eyes.
Oh, this is how I can see you.
The children may not have understood exactly what they were doing to figure out the mirror challenge, but with some trial and error, they did it. The children have demonstrated what science books call a law of reflection. The angle of the incoming light is equal to the angle of the outgoing light. So if we shine a light on a mirror from an angle, it reflects at the same angle. Let's look at this another way. In this demonstration, we're using a shallow water table and a slide projector as a light source. If we shine light on this mirror, the light is reflected. As the angle of the incoming light changes, the angle of the outgoing light changes by the same amount. The light does not spread out as it reflects from the mirror. Here we have a protractor so that you can see that the angles are indeed the same. In this representation, we can follow the path of light and see that the angle of the incoming and the angle of the outgoing light are the same.
So how does that help us to explain why we see ourselves in mirrors? You noticed in the demonstration that the light reflecting from the mirror does not spread out or get scattered in all directions. It stays in a narrow path. Because mirrors do not scatter light, the image is maintained, and this allows us to see ourselves in them. We visited the De Cordova Museum in Lincoln, Massachusetts, where William Harvey is exhibiting one of his sculptures. He's been working with mirrors in his art for quite a while. Let's take a look.
We're at the De Cordova Museum in Lincoln, Massachusetts. This is my sculpture, Marble Reflections. For the last 10 years, I've been doing a lot of work which is called environmental sculpture. It has to do with, well, the environment, with nature, with landscape, with light. The thing that's very different about this work is the polished stainless steel, in other words, the mirrors. The sculpture is made so you can walk around within it, and you can look at these reflections. You can see the light changing. You can see the imagery of the landscape, the views of the landscape in these mirrors, and you can see it all changing. It becomes part of the sculpture, and the sculpture becomes part of the environment. The person who is looking at this work of art is interacting, and not just the person, but everything that's around it, the trees and the sky and the landscape. In the polished stainless steel type of mirror, there's no layer of glass in front of that reflective surface. So that's called a first surface mirror. And the light reaches that surface directly, going through the air, bounces off it, comes back through the air. the design process really involves what's going on between these little blocks of stones and their mirrors and the spaces between them. This is one of the really fascinating things about a mirror in the landscape. You might expect to see a chunk of stone. Instead, what do you see? You see a mirror, and you see a wholly different view of something that you didn't even know was going to be there. And instead of seeing the stone, you see what is kind of like a big hole in the stone. I notice that when people come here and look at this, they stand here for a minute, then they run over there, then they run over there, and they keep looking around at all these different reflective surfaces, and the way the light is reflected off these surfaces is different. Sometimes the surfaces are reflecting the person or other rocks or the landscape. So it's quite varied. What happens is sometimes you have direct sunlight shining on the mirrors. The sunlight comes in, it hits the surface, and it bounces off it at the same angle that it hit it. And so you look in the mirror and what you see is over there. It's environmental art in the sense that the environment, which is all around it, is really part of the art.
You can see your reflection in a spoon, mirror, water, window.
You'll look at yourself in the mirror and you'll see the background, but when you look at yourself in the lake, you will only see yourself, no background.
Sometimes I see myself in the window when I look at it. When you open the light, it's light, you can see everything. That's because when I look out, I can see out.
Because the window's clear.
Sometimes when I look in a little, I can see myself.
There's nothing in the back of it to show a reflection, so if you can see a reflection, but you can still see through the window.
Because the sun's shining down to the water, and I'm near the sun, where the sun's shining down the water, and I can see my reflection. And when it's dark, you can't see that much. You can see like shapes. Because the sun comes, and when it comes and your window's closed, you can see yourself through it, and because of the sun.
I see my reflection, and I can see what's in back of me.
Earlier we said that all objects reflect light. So then why don't we see our reflection in this plant or in this duck? Let's go back to our water table demonstration. Light hitting the mirror is reflected without much scattering. Only one number is brightly lit. If we replace the mirror with this card, the light still reflects. However, if you look at the numbers at the side of the water table, you'll see now that several are illuminated. The light reflected from the card has spread out. When light reflects from a surface that is rough, it is scattered. But when light reflects from a mirror, it is not. The reason for this difference is that mirrors and shiny metals and glass all have very, very smooth surfaces.
But many of the objects we looked at seem pretty smooth. The poster, for instance, or the card we used in the demonstration appear to be smooth.
To our fingers, paper feels smooth, but to a photon, it's actually rough. Let's take a look at a piece of paper under a microscope and see. When we magnify paper, we can see the individual fibers that it is made of. With this magnification, paper doesn't look smooth at all anymore. So to a photon, paper is rough. And although a single photon will still obey the law of reflection, since the paper is not smooth, photons that hit this paper would bounce in all directions. Let's see what happens when photons hit a smooth surface and when photons hit a rough surface. This time, we'll be using ball bearings to represent the individual packets of light energy, photons. When we drop ball bearings on a smooth surface, like this piece of tile, they bounce straight back up at the same angle that they hit the tile. And when we drop them on the underside of a tile, the rough side, they scatter. But the law of reflection, that the angle of the incoming light is equal to the angle of the outgoing light, still holds, as we see if we follow the arrow on the rough surface. Here it is again. When we drop ball bearings on a smooth surface, they bounce straight back at the same angle that they hit the surface. And when we drop them on a rough surface, each individual ball bearing bounces back at the angle it hit the surface, scattering them in all directions. If we could look at a mirror under a microscope, we wouldn't see fibers or rough areas. So we see ourselves in mirrors because photons are not scattered. We see the card because photons are reflected from it, but now the reflected photons are scattered, and this prevents us from seeing our image.
Now that we've examined reflection, let's use it. If you have a mirror on the wall and no one is standing in front of it, where could two people stand to see each other in the mirror? Can you position 3 people so that they can all see each other? Why don't you try it? If you don't have a mirror available, draw the scenario. Develop your picture or explanation using the law of reflection. Polished metal, glass, like my glasses, and still, clear water all reflect light in a way that enables us to see ourselves. As you've looked in a shop window, you've probably noticed that you can also see yourself reflected in the glass. In fact, on a bright day, it's often hard to see what's in the window because you see so much of yourself reflected in the glass. Glass does not reflect as much light as a mirror does. It wouldn't be any good as a window if it did. Light is partially reflected from the surface of the glass. A small fraction of photons get reflected and the rest pass through the glass, allowing us to see what's on the other side. A way to test this is to place a piece of plexiglass in the sunlight. You'll see that a shadow is formed. So the light that isn't passing through the plexiglass is being absorbed or reflected from the surface of it. This phenomenon was used in a rather interesting way in the 1900s in the theatre to make ghosts.
In 1862, a retired English civil engineer, Henry Dirks, invented a way to create the illusion of a ghost on the stage. He lit an actor under the stage dressed as a ghost. Dirks then placed a large piece of plate glass at the edge of the stage, leaning out toward the audience at about a 45-degree angle. The ghost was reflected off the glass toward the audience. The actors on stage, behind the glass, couldn't see the ghost. The audience could, but not the glass. Dirks' idea was so successful that he sold the illusion to John Henry Pepper, and it was used on English and U.S. stages, known popularly as Pepper's Ghost. This illusion can currently be seen in the haunted house at Disneyland.
The reflective surfaces that we've explored so far today are flat, but as you know, there are also curved mirrors. A spoon acts as a curved mirror.
Sandra, Sarah, if you tilt it at a certain angle, look, you can see your feet.
Yeah. From the curve, the way the curve is.
Right.
Yeah.
The curvature of the spoon, you can actually see your feet. It's interesting, Sandra, that if you, Sarah, if you tilt it,
Find reversed.
So your fingernail on top.
Right side up.
Right?
now I'm right side up.
Her hands are right side up, yeah.
Yeah, stand on your head.
Now, Don and Peggy thought that the image was...
I'll look up upside down if it's concave, yes.
Angle of that doesn't. That's why you're.
To understand how light reflects from a curved mirror, we set up a water table and have two beams of light from a slide projector. Instead of using a whole curved mirror to reflect these beams, we use two flat mirrors placed at angles as though they were in fact part of a concave mirror. Each beam of light hits one of the mirrors and is reflected, so the incoming angle of light is the same as the outgoing angle of light. Since these mirrors are part of a concave surface, the reflected beams of light cross each other. If this mirror were complete, light beams would reflect from each point of the mirror and all the paths of light would cross. This is what causes reflections to appear upside down in a concave mirror, like the inside of a spoon. We use large curved mirrors and telescopes to collect more light from faint objects than our eyes can see.
Let's see how curved mirrors, much bigger than spoons, are used for astronomy. We visited Kim MacLeod, an astronomer at the Whiten Observatory at Wellesley College. She showed us how reflecting telescopes work.
Well, your eyeball is a small thing, and in space, distant galaxies and stars are very faint. And to be able to see these faint things, you want to be able to collect as much of the light from these objects as possible. And your pupil maybe only opens about 1/2 centimeter and lets in 1/2 centimeter's worth of light. But if you can be clever and build a tool that can collect more light than just this, then you'll be able to see fainter objects. Even on this little model telescope, you can see that there's a big area over which to collect light. And if you want, you can think about telescopes as being a photon bucket, a light bucket. If you have a small pupil, your eye, you're only going to collect a few photons from a star. But if you have a much bigger collecting area, a much bigger bucket for light, you're going to be able to collect more light and see fainter objects. If we have starlight coming into the telescope, we can bring it to a focus with a curved mirror, just the way that a spoon gives you a little image of your face when you stare into it. So if we can have a little image, we can take a picture of the star like that. And that's really why we build telescopes.
You may have noticed when you put a straight straw in water, the straw will appear to bend where it enters the water. You can see this bend if you look at the straw from the top or from the side. When you look from the top, the bottom of the straw looks closer than it actually is. When you look at the straw from the side, the straw appears to be broken at the water's surface. Now, although all forms of light travel at the same speed in a vacuum, as light travels through different transparent materials, like water or the air between the bowl and our eyes, its speed changes at the point where the materials meet. Of course, we see this straw because light is reflected from it. Light is traveling from the straw through the water at one speed. When it meets the air, the speed changes. In this case, the speed increases, and it continues to travel at this new speed until it reaches our eyes. When light photons pass into a new transparent material and their speed changes, their path is changed. This change in the direction of the light photons is called refraction. Let's look at some refraction effects that our children explored.
Can you see the penny? No. Can you see it? No. Pal? Mm-mm. Al, can you? No. Can you see it? No. Now? Yep.
Here we see that the penny has not moved. It is the refraction of light that causes the penny to look as though it has moved. The penny appears higher in the dish because the light is refracted as it moves through the water and the air.
As the French mathematician Fermat first suggested, light takes the fastest path it can between two places. Light travels slower in water than in air. So if light travels partially through water and partially through air, the faster path may not be a straight path, but a path that is shorter through water and longer through air. Now, it's rather like a lifeguard who is standing on the beach and sees someone in trouble in the water. It would be faster for the lifeguard to reach the person by taking a longer route on the beach and a shorter route through the water. The faster path may not be a straight path, but a path that is shorter through water and longer through air. As with the light, The fastest path for the lifeguard may not be the shortest.
Now let's visit Averill Elementary School in Lansing, Michigan, where Deb Smith from Michigan State University is working with Pat Christensen's 5th grade students as they discover refraction while exploring the path of light through air and water.
I'm going to hold this up so everybody can see it. There's this special box, and it has a card with slits in it. So think about what you think might happen to the light. And if you look inside, the light will be coming in this way, and you can sort of trace on the bottom where the light is going. Then, what happens if you put just an empty plastic glass in the light inside the box? What do you think will happen? So you need to write that in your journal, draw a picture, and make your prediction and say why you think so. Trace the path.
Except for the water. Let's see.
Beams. How about if you set that down very slowly in the 2 beams and see if anything happens to the path of light?
See, it's just like it.
Is it still going through?
Huh?
Yeah. Still going through?
It's right on the bottom. See, it's through the bottom of it.
Okay. So why don't you guys do your drawing and writing about what this one did? I'm going to go get you some water.
The children predicted and saw that light travelled through the hole in the box and reflected off its far wall. But they were surprised by what they saw when they placed the transparent cup in the box. Light was now reflecting off the side walls of the box too, although most was still passing straight through. But when they added liquid to the cup, they saw a very different effect. Let's take a look at the Michigan children's explorations again.
Like those other lines that used to be there disappeared and morphed into an X.
Into an X. Okay. So we have the light straight on. But why is it crossing?
Because the water's like, oh, okay. Probably because the light is supposed to go straight, but since the water is blocking it and it's a round cup, probably can't go through it because then it probably wouldn't be visible anymore. So it'd go around and the rest of the light would go over here.
So you think
but you can see it in here if you look hard enough.
I know, that's where it is.
That's where it crosses once again, and then it crosses twice. Once in there, then out here.
Okay.
But like I said, it sort of looks like it goes around.
So you're thinking some of it might go around, and Jordan's
It's like
thinking...
the light's trying to travel around.
Okay.
If the light is trying to travel around, how come it's going into, like, where the water is? 'Cause
no, I mean, that's where it's, like, starting to come. I mean, because it might be, like, cracks under the cup.
So you're thinking it's, like, going under the cup?
Maybe that's the way it starts.
Okay.
Or maybe that's the shadow, because look at, when he lifted it up, it went right across.
Yeah.
So like on Back to the Future when he pulls that car out and the fire just comes right out of there. It's like boom.
Like exhaust coming out the back of the car.
Oh,
like the rockets. Yeah. What do you think is going to happen when you pour the water in?
I wasn't sure. I made a guess it would decrease the light. Okay.
Okay, stop. What has happened?
Oh, I see. It seems like the two pathways of light come like together and cross.
Oh. So which See where it crosses?
Mhm.
See how you've got the two beams again back here?
Mm-hmm.
Is this beam from this light or from that light, do you think?
Which
I
beam?
think it's from.
The one on your side, that one right there.
I think it's from
This
side.
one.
Yeah, from this one.
From
'cause
the
you can see it.
right-hand side one?
Yes,
Yeah, 'cause you can
because
see
they
it cross.
crossed.
Okay, so how could we test that? What would we do?
You can cover
Cover
up
on the
one of
side.
the.
Okay.
sections. Yeah, so they must go up across.
We're gonna test it with a different liquid.
Okay.
Okay? Here's the glycerin. Patrick, let's see what happens. Pour it really slowly. And watch the path.
Well, you can see the bars get sucked up, get shorter.
Yeah, as the liquid rises. So what do you think?
I had a prediction that it would kind of dim the light because of the thickness.
Mm-hmm.
And that was right.
Uh-huh. It looks dimmer back there, doesn't it?
And it also crosses like the water did to the light.
Yeah.
It looks.
Does cross.
It looks different than what the water did because.
Yeah, you don't have much of the reflection.
Yeah.
It's like the water
it doesn't
did.
reflect
Yeah.
as much. This just has a little bit of reflection back here.
Right.
And like the empty glass, you don't have the kind of the reflection up front of the water too.
Uh-huh. Okay, here's the vinegar, Nicole. Let's see what happens. Watch the path. Ah. Okay, that looks like it's enough. What do you notice?
It crosses again.
All the liquids we used crossed, and this one is it crosses farther away from the
But
cup than
still
the-
not as much as, still not as far as the water did.
The water came way out here.
Oh, okay.
I think the thinner the liquid is, the farther away from the cup they cross, because the water was way up here. The vinegar, of course, is right here, and the glycerin was way in here.
Mm-hmm.
The children noticed that the two light paths crossed on the far side of the cup. This happens because the light is refracted twice. The path of light changes abruptly when it travels from the air into the cup of liquid. And when it passes into the air again, it changes direction again. The point where the paths of light cross is called the focal point. Each liquid added to the cup produced a different focal point. These cups with the liquid are acting like a lens. Each lens has a specific focal point where the paths of light cross. Lenses are used all around us, in eyeglasses, binoculars, microscopes, and cameras. Just like the children's cups with liquids, the lenses in these instruments change the path of the light to help bring an image into focus. We'll explore the camera in more detail in Workshop 4. Telescopes also use lenses to focus on objects very far away. Let's go back to Whiten Observatory at Wellesley College and see one of their refracting telescopes.
Yeah, now this telescope is what most people think of when they think of a telescope. Well, we can telescope it here, you know, the traditional spyglass variety. And this telescope is like the big telescope behind me here at Wellesley College. It's a little different than the one we saw before. Let me show you what I mean. This telescope, instead of having a curved mirror to make an image of your stars, has a lens in the front. It serves the same purpose as the mirror. It collects a lot of light and brings that light to a focus, to an image that you can then look at or take a picture of, but it does it with a curved lens instead. Nowadays, you don't see many telescopes like this anymore. Now, all the big research telescopes are made of mirrors instead of lenses. And there are a couple of good reasons for this. It's very hard to make a big lens that's perfect. Now remember, the main function of a telescope is to be a light bucket, to collect more light. You want your telescope to be big. And making a big lens is tough. With a lens, the light has to go through the glass that the lens is made of. And if you want to make a big lens, that means you have to have a big, perfect piece of glass to start with. No bubbles or defects of any kind. And it's very hard to make a piece of glass that big that's perfect. And another reason that it's hard to make a big lens for a telescope is that in a telescope like this one with a lens, the lens is only supported by a ring around its outside. And when you turn the telescope this way or that, the lens, being only supported on the edges, can bend and flex and ruin your image. But with mirrors, you have the benefit that you're not looking through the glass, so you're only looking at a coating on the mirror's surface, so it doesn't matter if inside the glass there are small bubbles or defects, and that you're supporting it from behind. You actually sit the mirror in a cell that can hold it from behind and give it much more structure and support. So that's why most telescopes today are made of mirrors.
Refraction also helps us to understand certain natural phenomena, like mirages. A mirage looks like a pool of water in the distance, but as you get closer, it vanishes. Now, people don't just see mirages on the desert when they're dying of thirst. You may have seen this effect driving along a highway on a very hot day. In front of you on the highway, you see what looks like water, but because it hasn't rained, what's really happening? Well, some of the light from the sky far out in front of you is bent. It's refracted as it goes from the cooler air into the very hot layer of air just above the highway. So what you're actually seeing is light from the sky. Although it looks as if this light might be reflected by the road surface, the light is actually refracted by the layer of hot air just above the highway. As you get closer to the mirage, the angle from which you are looking at it changes, and you can't see the mirage anymore.
Today, we've been exploring how photons travel when they meet different materials. Light photons can be reflected from smooth and from rough surfaces. The path of the light can be changed when photons pass through transparent materials. This is known as refraction. But photons can also be absorbed by materials. When this happens, their energy is transformed within the material. In Workshop 3, we'll return to reflection, refraction, and explore absorption as we look at colour. And we'll also look at light that is not visible to our eyes.
Thank you for joining us today. Don't forget to check out our website for additional information, activities, and discussions with your colleagues. The address is www.learner.org/channel/workshops/shedding light. You may want to bookmark this address for easy access. And if you don't have access to the web, you can share your thoughts with us by email, fax, or regular mail. Our email address is channel@learner.org. Our fax number is 617-496-7670.
Annenberg Media. For information about this and other Annenberg Media programs, call 1-800-LEARNER and visit us at www.learner.org.